Okay, so, here we are, we're back. We're oscillating. We talked a little about ways of ruling out limit cycles and closed orbits, Dulac's criterion, and we talked about Poincaré-Bendixson theorem. I sent you, or actually I posted a history of the Poincaré-Bendixson theorem, which as I reread it is not very readable or good. But you could take a look. And there's also a proof of it, the Poincaré-Bendixson theorem, on the resources part of Piazza, if you want to look at that. That has some historical interest because it's the notes that I took when I was taking the course about 30 years ago. And it includes my little handwriting where you can see where I'm confused about what the teacher is saying. So that you may find that entertaining. All right, but anyway. Our topic now is, again, looking for closed orbits, but in a very famous system that was one that was real important in the development of the subject, called the van der Pol oscillator. Which looks like this. It's x double dot plus a constant mu times x dot times x squared minus 1 plus x equals 0. So a few words about this. Van der Pol, that's Balthasar van der Pol, who was Dutch. He was an electrical engineer, I think in the early part of the 20th century, maybe around 1920 or 30, working at Bell Labs in the early days of radio. So radio at one time was a cutting-edge technology. And they used things in there that were the forerunners of semiconductors and transistors. They used what were called vacuum tubes. Some of you who are music lovers might know about vacuum tubes because I've been told that audio types like them for some reason. Yes? Why? The sound that comes out of the loudspeaker is somehow different? For guitar amps, because what, it has a little bit of noise in it and it sounds organic or something? Yeah, this sounds less digital. Okay, right, so I remember vacuum tubes because as a kid, when our TV used to break, which it did frequently, which doesn't happen anymore, there was a guy who would show up with a bunch of vacuum tubes, and he would, and also the TV used to glow. If you would look in the back of the TV, there was all kinds of light coming out of there, which was these vacuum tubes radiating, and he would go in and take out the tubes and put in new tubes. So anyway, they were the power source for all kinds of devices in the old days. And van der Pol wrote down a very simplified model for vacuum tubes that were powering early radios. Anyway, so you'll notice it looks a lot like a simple harmonic oscillator. The first term and the last term would just be simple harmonic oscillator, which you might remember from elementary physics. When people are talking about LC circuits, right, with inductors and capacitors, you get something equivalent for the circuit equations to a simple harmonic oscillator. But then there's this funny nonlinear damping term here, which has to do with some nonlinear aspects of the vacuum tube. I think it has a nonlinear inductance, if I remember right. But anyway, this introduces all kinds of interesting complications to a simple harmonic oscillator, this nonlinear damping. That is, notice it's damping, it has x dot. But normally, you're used to damping that's just a constant times x dot. Here, we have this extra term that makes it nonlinear, x squared minus 1, which notice can have either sign. It could be positive or negative, depending on if x is bigger than 1 or less than 1. And so when x is big, say bigger than 1, this acts like ordinary damping that tends to make oscillations decay in their amplitude. But if x is less than 1, then this term is negative. That means you have negative damping, which you might not be so familiar with, but negative damping means pumping. right? Negative damping pumps energy into a system. So if you imagine the oscillations damping out and getting to lower amplitude, when they get too low, this term kicks in as negative damping and pumps them back up. So it might seem plausible that this would settle down to some oscillation of a given amplitude, and that's what it does, but we want to understand that oscillation. So first thing is that using Poincaré-Bendixson style arguments, which I don't want to go into here, they're pretty elaborate. We can show that there exists a unique, so with this exclamation point, I already discussed, that means there exists, the exclamation point means unique. So we can prove that there exists a unique limit cycle. For this system, for all values of the parameter mu positive. Okay, it always has a limit cycle, and it has exactly one limit cycle. It's not just a closed orbit, it really is, in fact, it's a stable limit cycle. So all that can be proved, but it's fairly nasty in that the trapping region is complicated, more than the trapping region we looked at in the last lecture. And I don't want to go into that. But you know, there are books that I refer to in the text if you want to look up the proof. But instead, let's focus on two limits where we can see pretty clearly what's going on. That is, the most instructive case, or cases would be, let's investigate the limits of either very small or very large mu. Actually, very large mu is in some ways easier. Let's do that first. So that's extremely large nonlinearity, this nonlinear term, big, or small. And see what we can see using perturbation theory or some other kind of reasoning. So section 7.5 in the book is about the case of mu large, which leads to phenomena that are called relaxation oscillations. So I want to, once we get to the right point in the analysis, I'll clarify why are these called relaxation oscillations. But for now, let's just see what we can do. Is there any questions so far? Okay. So we're doing the strongly nonlinear case. And the solution method we're going to use involves a very tricky change of variables. Which people refer to as the Liénard transformation, after the person who thought of it. And the upshot of it, just to sort of give away the punchline, is that after we make this Liénard transformation, what's good about it is that it causes the limit cycle to approach a constant shape. As this parameter mu gets large, as mu goes to infinity. And this property that the limit cycle, which you know in general will depend on mu, and as you keep changing mu, the limit cycle will change in its shape. Under this trick, it doesn't change its shape, it approaches a certain shape, and that just makes the analysis much easier. It also makes it very intuitive that the system has a limit cycle. You'll just be able to see it clearly in the picture. All right, so let me show you the transformation. And also try to motivate it a little bit. So first look at the first two terms in the equation, x double dot plus mu x dot x squared minus 1. Just eyeballing that, you know, like ask, is that equal to something simpler? You might notice that it's a perfect derivative. That is, it's d dt of something. It's d dt of x dot plus mu times 1/3 x cubed minus x. Right? Because if I differentiate the 1/3 x cubed minus x, this becomes 3x squared x dot minus 1, and the 3 cancels with that 1/3. And also then there's the chain rule term, the x dot, which appears there. So, okay, so we've written those two terms as d dt of that expression. And this suggests a nice change of variables, which is we're going to take that whole thing in the big parentheses and call it a new variable w. Let w equal x dot plus mu capital F of x, where capital F of x will be our shorthand for this function here, the cubic, 1/3 x cubed minus x. Let me point out one thing here that's a little different than what we're used to. We've sometimes done problems where we, like normally when we have a second order equation like that, x double dot equation, we make a change of variables y equals x dot. Right? We've been doing that a bunch of times. This is not that transformation. This is more complicated than that. We're not just saying w equals x dot. We're saying w equals x dot plus this other term. So this is not the standard transformation. And if you do the standard transformation, the analysis is much harder because the limit cycle keeps changing its shape, and you'll see it gets very long and stringy looking as you make mu large. So it's a bad transformation, the usual one. This one is beautiful and really works well. Anyway, with this change of variables, then w dot, well, what is w dot? That's just, I mean, this whole expression in here is w. So there, you know, if you then look at the van der Pol equation, it says that the first two terms, which is this d dt of w, those first two terms equal negative x if I take the x to the other side. So w dot is minus x from the van der Pol equation, which I will abbreviate VDP, van der Pol. So we now have our little system as a first order system. That is, the second order equation has been reduced to x dot equals w minus mu f of x, and w dot is minus x. That's equivalent to van der Pol's equation. Any question about the algebra so far? Okay, so there's our little problem. We're going to try to analyze it in the phase plane. And we've seen earlier that it's helpful to look at null clines in thinking about trapping regions and such. So let's look at the null clines for this. So here's the XW plane. Anything wrong? You want to ask anything? No? All right. So how about if we look where x dot is 0? X dot is 0 when w is mu f of x. And f of x, remember, is just this function 1/3 x cubed minus x. So that's a typical looking cubic. It would be something like this. And then over here it's symmetrical. And we know that on that curve, that's where x dot is 0. That is to say, the vector field is vertical there. Right, all the vectors cross that vertically. We haven't decided yet whether they cross up or down, but to figure that out, we have to look at what is w dot. And so when x is positive, w dot is negative. That means that we cross over here down through that null line, and on this side we would cross up. Okay. Next, let's just label a few points on here because we're going to need some properties of this cubic curve. If I calculate the minimum, it turns out to be at 1. And you can check that the value at the minimum, so down here, this is 1, and it has a y or w coordinate of minus 2/3 mu. That's this point. And it's also going to be convenient to look at this one over here. By symmetry, this one is at minus 1 comma 2/3 mu. And other points of interest will be, what if we go on a horizontal line over here, staying at 2/3 mu, where do we hit? It's not clear yet why we care about that, but you'll see in a few minutes. This point turns out to be at an x coordinate of 2. And I'm going to label that as point A because we're going to be talking about it a fair amount. And this point down here I'll call B. Okay. Now, you might notice some things, which is that if you look at some of these key points that have been labeled, the x coordinates are of order 1, 1, 2, -1, whereas the w coordinates have mu's in them. Right? They're all proportional to mu. And remember, mu is gigantic. Mu is 100 billion. You know, we're letting mu go to infinity. So this is a kind of a weird picture where everything in the w direction is gigantic, scaling like mu as mu goes to infinity, whereas in the x direction it's independent of mu. So that suggests an obvious thing to do, which is rescale, because you don't like to deal with big numbers, especially when mu is going to infinity. We want the picture to become invariant as mu goes to infinity. And so I'm going to rescale everything in the w direction by mu. Hopefully that seems like a reasonable thing to do. So now we're going to let y equal w over mu. And if you do that, this makes the y variable be order 1 for a large mu, which is just more desirable. Okay, so in terms of this definition of y, let's rewrite the system. Now it becomes x dot would be, we can factor out mu because w is mu y. So it's now x dot is mu times y minus f of x, and y dot, well, since w is mu times y, it looks like we're going to get y dot is minus 1 over mu x. So this is our system now. Yeah. Okay, so far? Okay, now it's going to be easy to see what's going on. Let's just keep in mind that mu is an enormous number. So this is telling us that x dot is going to be very large. It's of order mu. that is velocities, thinking of x dot and y dot as velocities in the phase plane. X dot is big, and y dot is small. It's of order 1 over mu. So what that means is in the xy plane, the trajectories are basically just going sideways at lightning speed, right? Because x dot is very big, and during the time that x is moving, y dot is only moving at velocity 1 over mu, which is tiny, so it's barely going down. It's basically shooting sideways all the time. And so that makes the picture easy. Let's just redraw things. Also, maybe we should notice one other little detail up here, which is that y dot is negative when x is positive. So tending to go down a little bit. But remember, it's a small number, y dot, but it is small and negative. All right, so here's our picture in the xy plane. Draw the cubic fairly big because you're going to need room. And so now start somewhere and see if you can figure out what's going to happen. Suppose we start there. Then, as we said, the first thing that happens is x dot is gigantic because, oh, actually, let's be a little bit careful. I said x dot is order mu. Now, that's true if y minus f of x is order 1. Right? That is, if we're not on the curve, if we're not on the nullcline, y minus f of x is some number of order 1, and then x dot will be gigantic. However, if y minus f of x is very close to 0, so that we're essentially on the nullcline, then it could get a little tricky, because then you have a big number times a small number. Right? So in particular, when y minus f of x is order 1 over mu, canceling out the mu, then we might have to think carefully, because x dot would be order 1. So, but that's only going to occur in a thin, thin, thin ribbon around the nullcline. Right? We're basically on the nullcline, only order 1 over mu away from it. So for now, we're not there. So all we have to do is just go, we're going straight sideways till we get really close. Once we get really close, now we have to start thinking and realize that we can't actually hit the curve going sideways, because on the curve, we know that this is a curve where we go down. Right? That was what happens on the nullcline. So the motion is that you go zap essentially onto the curve and then go down below the curve, and now you're on the bottom of the curve. And what happens next? Well, y dot is negative, so you're going to keep going down, and you're going to hug the back of this curve all the way down to the bottom. Now, you might ask, well, what would happen if I came off the curve? Well, there's a tremendous wind blowing at, 1,000,000 miles an hour that way. So you can't get off the curve, really. I mean, you can get order 1 over mu away from the curve, but essentially you hit it, go down below it, and then just you're pinned on the back of the curve until you get to here. There, the wind blowing 1,000,000 miles an hour, once you get to the bottom, well, now you're not pinned against the curve anymore, and you can just be blown all the way over to here, which is what will happen. At which point, again, the same scenario happens. You're going to come close, go onto the back side of this curve, and then keep in mind, we're going to go very slowly oozing up this curve. This is all happening slowly because motion in the y direction is slow. So if we do it with sound effects, You know, it would be like zap over to here, and then, you know, taking a really long time to go down. So why is it a relaxation oscillation? Well, I think the way that people were imagining it is that there was some kind of stress that was building up. And like in earthquakes, let's say, where crustal plates are grinding against each other, you know, and it's really slow, and then suddenly something pops, and then there's an earthquake on a fast time scale. And all that stress is released quickly after a very slow buildup. So it's that sense of relaxation. I'm debating with myself, but I can never resist. So I'm going to go into X-rated territory here for a second. You might be familiar with a relaxation oscillation in your own sexual response. This has been studied in the laboratory because people study all kinds of things. And so researchers got people to be wired up with what are called, what would be the term? It's the thing that measures electrical activity in muscle. Electromyograms, maybe? Something like that. Anyway, so you can measure the electrical and neural response in a person's body as they're having an orgasm, and that has been done. And there is relaxation oscillation behavior, slow build up, fast release, no surprise. But anyway, that is that is a real thing in our own lives, and is also, you know, in earthquakes and other. You know, another case where this is relevant is in bowing a violin string. So you might have heard of stick-slip oscillations, where you're sort of dragging the bow across the string, and then there's a sudden slip of the string. So it's an important thing in music, this kind of nonlinear oscillation. Anyway, okay, so here we are with this system. And so notice that we've basically shown that there's a limit cycle, and we see what the shape is. That is, starting from any initial condition, after a very short time we hit this, and now we're essentially on the cycle because we just go around, and we're on it. This is just going to keep repeating. So there's very short transient. Yes?
How are we certain that it will cross the curve and not hug it on
the question was, how are we certain that it will cross the curve and go on the bottom, the back side of the curve? Yes, why couldn't it go down on the inside of the curve? Well, one thing is you can tell that by looking at the equation for x dot. Okay, so x dot, which is mu y minus f of x. X dot is negative if y is less than f of x. I should say if and only if. Right? So that is to say, notice that the shape of this limb is one where, as you're going down it, x is becoming less. You're moving to the left. And so the only way that x can be decreasing is if y is less than f of x. That is, the point, the phase point, has to be below f of x. Otherwise, you couldn't be moving to the left. There's no way to move to the left while staying on this side of the curve. Yeah. Is there another question? Okay. So anyway, so that's the limit cycle, this interesting shape. Now, you can also draw it as a, well, also you can see intuitively that this is stable by that wind blowing argument that I gave. And all that can be proven, but I think it's believable. Okay, now, the other thing, and also the uniqueness, I hope, is obvious. That if you're anywhere, this is the picture that will quickly ensue. There's no other possibility for a limit cycle. Now, as far as the waveform, if you want to graph x versus time, let's think about that. Well, okay, so why don't we start at that point I numbered as A, where x was 2. So here we are at A, at 2. There's 0. Let's put -2 down here. And what's going to happen? That is, well, we're slowly, this was A up here. We're going to very slowly decrease in x down till we get to here. That's where x is 1. This is x equals 2. And so what's going to happen is something like this. All right, here's 1. So we have this slow decrease till we get to 1. Then, on a very fast time scale, once we get down to here, we just shoot across over to x of negative 2. So on this picture, it will look basically vertical. And then the same thing happens. We're going to go slowly like this till we get to negative 1. And then zap, almost vertical, back up to 2, and so on. It's just going to do that. So this is a sawtooth wave. It's a kind of sawtooth wave picture. Very far from a sine wave. It's a very nonlinear object. And we could also estimate some timescales that we know that, if we say, like, what's the period of this to go from here back to here? Well, you can see it's dominated by the slow parts. I mean, it's basically going to be this time plus this time. There's almost no time spent in the jumps. And so taking the lion's share of the period as these two contributions, how long is it going to take to do this? Well, that's not hard to figure out, because just think about the y velocity. The y velocity the whole time was order 1 over mu. Very slow. And you've traveled a distance in y of order 1. You went from a y of whatever this was up here, 2/3, down to whatever, something else, negative 2/3. Yeah. So whatever. I mean, don't worry about the details. You went some distance that was of order 1 at a speed that was order 1 over mu. So distance equals rate times time. This will take time mu, which is a large number. So this is of order mu to do this. And this fast part, the jumps, take time. They require a time of order 1 over mu, which is very short, negligible. So anyway, from this, we can expect that the period of the oscillation is going to be order mu. But we can actually calculate the period. We can calculate the coefficient, what is the constant multiplying the mu, by a little argument that I want to show you now. And that's the leading contribution. Maybe I should say before I forget that if you wonder what's the correction to this, that thing we're about to calculate, it's not the correction due to the time it takes on these jumps, this order 1 over mu. There's actually another time scale, which is a slow time scale to turn around the corners at places like this and like this. This one especially is important. So in the book, I quote a very fancy asymptotic calculation where the time required to go around this corner is calculated in terms of something called Airy functions, which if you take a asymptotics course, you'll learn how to do that. Here, it used to be the course called TAM 6130. We haven't offered it for a while. But I teach it once in a while. So if you want to see the correction to the thing I'm about to show, that's a pretty elaborate calculation. Anyway, so let's just get the dominant term here. Oh, I guess I can erase this side. Okay, so estimate the period. Well, as we said, the period is approximately 2 times the time to go from A to B. And we know that when we're going from A to B, this place down here, that we're essentially on the null cline. We're a little bit off by order 1 over mu or some small quantity like that. But if we're just trying to get an estimate, we can pretend that W is equal to mu f of x. use the fact that W is approximately mu times f of x. That is to say, we're essentially on the null line the whole way down. And then, how does that help us? Well, the period is going to be 2, the integral from, whatever the time is when we're at A till the time when we're at B, dt. And now we can rewrite that somewhat cleverly as, that is, we don't have access to dt itself, but we do know x. We have good control over x. We know that x went from 2 to 1. And so the x value at A is 2, and the x value at A is 1. And so we convert this into an x integral. That is, let me put a dx out there. Now, how can I make a dt into a dx? I could go dt over dx, but that's not going to bring in the null line information. A better way is to go dt over dw over dx, where the magic of the chain rule and this Leibniz notation shows that everything cancels out and we're getting dt. And these are quantities we can calculate because this first term is just 1 over w dot. And this term is dw dx, but we know we're going to use this fact relating w to x on the null line. All right, so let's crank that out. Okay, so we have w dot, the first contribution. W dot is just minus x. And so 1 over w dot is minus 1 over x. And the other term, dw dx, well, that's just d dx of, well, we said that w is essentially mu times f of x. So that's our approximation there. And that's going to give us mu f prime of x, which, if you remember the definition of f of x, it was a third x cubed minus x. So this would be mu times d dx x cubed over 3 minus x. So it's mu x squared minus 1. And then combining that with the w dot and using this formula up here, we get t, the period, is approximately 2 integral minus 1 over x mu x squared minus 1 dx, integrating from 2 to 1. Oh, let's see now. Hold on. Well, maybe did I mess that up earlier? I did, didn't I? Here, in this formula, I should have said the time at A, my x was not 1, my x was 2. Right? So I had that upside down. But it would be correct if I had a negative sign. Right? Yeah, because I started at the wrong place. Sorry. Yeah. So let's put a negative there. Then it's OK. And so over here, I'll put this negative. And then I have to switch them again. But that's OK. Let me just write it out. OK, but just you can check that I've done the negative signs right. What you end up getting is 2 mu times, you can do both these integrals, because x squared over x, that's just x, that integrates to a half x squared. And this other one is minus 1 over x, that integrates to log. And we go from 1 to 2. And I'm pretty sure I did that okay. Did I? Or is there a negative sign somewhere? So here you're saying in order for it to be right, I have to do this? I think that's... Yeah, but so I have negative 2 times that negative 1. Excuse me. So I think those cancel, and then this should be right. Is that right? I think so. No? Still wrong. All right, hold on. I know that the answer is supposed to come out 2 mu 3 halves minus log 2, which is positive and which is order mu as expected. But I don't know. I think it's okay. No? Yeah, it's good. All right. But anyway, this is the period to leading order. So any question about this calculation? Yes? Why is W approximately mu f of x? That's the statement that we know the shape of the limit cycle. We know that the curve, this is a nullcline right here, W equals mu f of x. Well, I mean, in y notation, it would be just y equals f of x. This curve in W coordinates is W equals mu f of x. And so I'm just saying that on the limit cycle, I'm basically on that curve. I'm a little bit off, but it's invisible. Does this mean that x dot is approximately 0? Well, well, yes, kind of. But that's a bit too crude to say that x dot is 0. I mean, yes, it is approximately 0 in the sense that we're moving very slowly in x. That's true. We are. But, you know, I mean, it's not so helpful to say it like that. Yeah.
So when we define x dot, it's like x dot equals to w minus mu f x.
You say when we define x dot, it says x dot is w minus mu f of x, yes?
Right, so that means that the point is moving across, right across.
I mean, by the way, just to clarify your last question, what we really should be saying is that I mean, what is it that we think is going on? I think what we really believe is that on the true limit cycle, we have y equals f of x plus a small correction, which I don't remember what it is, but I think it might be of order 1 over mu, or maybe it's 1 over mu squared or something. I'd have to check. But it's something kind of like that. Well, we can think about it, can't we? Because we had... maybe I'll let you think about it. That is, try to figure out what is the right... There's some correction term here that's small, but it exists. And so when you earlier asked, is x dot, are we saying x dot is equal to 0? Not exactly. We're sort of saying x dot is mu times whatever order of 1 over mu this is. You know. So it's not 0. It's some small quantity. I sort of think that this might be right. But anyway, I'll let you try to check the reasoning on that. But anyway, back to your other question.
Yeah, so as x dot like is larger than 0, then w is larger than mu f x.
Well, hold on. If as x dot is larger than 0, W would be larger than mu f of x. That's right. But x dot is not positive over here. X dot is negative when we're on the limit cycle. When it's crossing, the only place where x dot would be positive would be on this part, or here when we're going up. Yes?
But since W is always larger than mu at x, when would it get over?
Since W is always larger than mu f of x, it's only larger here and here. Then it flips over here when it crosses through vertically, and now it's on this part. It's below.
But when it's about to cross, like when W is very, very close to mu at x,
Yes.
X dot is very, very small. So won't it be like hardly moving at all? So will it reach a stagnation point? And
Well, you're raising the issue that one needs to think very carefully about what goes on in this region. And that's what happens when you do an asymptotic analysis. You're right, that you do have to think carefully. I've been describing what in the jargon is happening in the outer region. That is, the region before anything gets complicated. Like in boundary layer theory, when we're studying problems in fluid dynamics, there's the region of the flow away from the boundary layer where things are easy to think about comparatively. And then once you get very close to the boundary, or in this context, once you get very close to the nullcline, you have to sort of blow things up with a microscope and look at what's going on. And you're right that, we're going to see some kind of transition where we're moving in a complicated way. We know we have to cross through here vertically. So, you'd have to really carefully analyze this, what's going on right in here. But it all works. It's just that it's too subtle for us at the moment. I don't want to do it here. But you're right that I've been a little glib about this. And so it's slightly mysterious given the presentation I've given. But it's not wrong. It's just I'm leaving some things out. And you can believe it, right? I mean, you know that it's got to be horizontal here. It's got to be vertical through the nullcline. We're going down this direction along the back of the nullcline. All that is clear. But how everything matches up is a little tricky. Yeah. Okay, so I think I'm ready to leave that topic. That was the van der Pol for large mu. Now let's start talking about it for small mu. And that is another whole different regime. Actually, I think we can, sorry, I'm just a little bit staring at this. I think we can decisively say that this is the answer for the deviation, can't we? Because didn't we have, in our governing equations, we had x dot was, what was it? Mu times y minus f of x. And y dot was something like negative x over mu. Is that right? That's right, right? So this is of order 1 over mu. And so when we're moving on the nullcline, or essentially on the nullcline, if we had y equals f of x plus order 1 over mu squared, let's say some constant in here, then when we look at the x dot equation, what would I have? X dot would be it'd be mu times something of order 1 over mu squared. This would be order 1 over mu, which would be comparable to the y dot. And that would allow us to make a transition like so, where I'm starting to move on a 45-degree angle, right? Where I go from being horizontal to going vertical. I have to be in some place where y dot and x dot are comparable in size in order to go at an angle, right? And so I think that's telling us something about the thickness of this layer around here. It's when does x dot and y dot become comparable? They become comparable in a ribbon of thickness 1 over mu squared, as you could sort of see from this argument. Anyway, you could look at it more carefully if you're really interested in that. But it's a fine point. This was the main point. Okay. So van der Pol for the weakly nonlinear case. That is, we're now talking about mu much less than 1. This is discussed in section 7.6 in the book. And this part of the analysis is really kind of different from the rest of the course. It's one of the few times that we'll be doing math the way you might think of math. That is, formulas, lots of formulas, equation manipulating, not so geometrical. But okay, maybe that comes as a relief. Maybe you like that better. So anyway, we'll do some of that now, and I think we'll have to finish it in the lecture after the test on Thursday. It's a pretty long job to analyze this. So since we have this small parameter, let's think of it as epsilon. That is, that looks like a small parameter. So it's conventional to write this as x double dot plus x plus epsilon x dot x squared minus 1 equals 0, where the epsilon is greater than or equal to 0 and much less than 1. And first, just to get some intuition about what you should expect, keep in mind that when epsilon is strictly equal to 0, then we just have an ordinary harmonic oscillator. I didn't say anything, by the way, about why have we've got no frequency term in front of the x, and it's because we've chosen units of time so that the natural frequency is 1. So we could always do that without loss of generality. Anyway, so we have this harmonic oscillator with a frequency 1, and we know that in that case all the orbits are circular because of the way things have been scaled here. And they have period exactly 2 pi. And if you want, by choosing the origin of time nicely, you can make it so that x of t is just a cosine t for some constant a. Okay, just cosine oscillations of constant amplitude, with amplitude depending on the initial condition. Now, what happens when we turn on this nonlinear damping? Now we've changed the vector field by an amount epsilon everywhere. Right? That is, if you think of the arrows, all the arrows, were pointing a certain direction. Now they have a little perturbation to them that's 1/1 billionth in their x and 1/1 billionth in their y. It's a very tiny change in the arrows. So you might believe that for small epsilon, you really haven't done anything noticeable to the vector field. You'd expect all the orbits to be nearly circular. Now, we've seen that centers are delicate, right? So a tiny change can make a big qualitative difference, and that is what's going to happen here. All the orbits are nearly circular, but they're not going to be exactly circular, most of them. They'll be spirals, but they will approximately repeat every 2 pi. Because, again, you've only introduced tiny changes to the vector, so you can't really change the period by more than some amount proportional to epsilon. That's what you'd expect. So still, we had that earlier theorem that I didn't prove, but that said this system does have a limit cycle as soon as epsilon is positive. So we could ask how to find the limit cycle and what's its amplitude. So here's one method, which we're going to come up with a better method soon, but maybe this is a good place to start. It's a crude method, but it's not so hard. Let's look at think like a physicist or an engineer. That is, we could say for a simple harmonic oscillator, energy is conserved. And so as we go around one cycle, the energy has not changed. And so you could ask, let's look at the change in energy over one cycle. Now, for this system with the epsilon in there, keep in mind that sometimes it's getting pumped and sometimes it's getting damped. That's what we said. That's what that interesting term does. And you would think that on the limit cycle, when the system repeats exactly, the amount of energy pumped in would exactly match the amount of energy dissipated. That's the condition for the cycle. That is, if you're bigger than that in amplitude, you're going to, on average, be losing energy more than you're gaining it. That's why you're damping down to the cycle. Okay, so it's this kind of power consumption argument that will lead us to an estimate of the cycle itself. So we should have, on a cycle, as opposed to on a spiral, on a cycle, we have delta energy exactly equal to 0. So that's going to be our criterion. The other trajectories have the change in energy either positive if they're on the inside of the cycle or negative if they're damping out from the outside of the cycle. All right, so use that little intuition. Now here, energy, remember, we're talking about the energy for the undamped oscillator. That's how we're using this physical argument. Everything is scaled so that that energy would just be a half x squared plus a half x dot squared. That's like potential plus kinetic energy in ordinary physics talk. And so then we can ask, how does that change? Well, its time rate of change would be xx dot plus x dot x double dot. And factor out the x dot, x plus x double dot factors out. And so using the van der Pol equation, x plus x double dot is then this damping term. So we put in a negative epsilon x dot times x squared minus 1. And so far everything is exact, no approximation yet. We're just defining the change in this quantity E for the van der Pol. Okay, now comes what a physicist would call an ansatz. That is, we're going to guess that x has a certain form. That is, we'll suppose x is essentially a cosine t, just like I assumed earlier, except earlier it was a fact. Now it's an approximation. That is, really we're saying that because we only introduced an epsilon change to the vector field, we expect the solution to be essentially what it used to be, still basically sinusoidal, but maybe with a little correction of order epsilon that we could worry about later with perturbation theory. And here A is a constant to be determined. That is, we're looking only for the cycle. We're not interested in the approach to the cycle. Just what A would have the property that the change in energy on that circle would be 0. That's what we're asking. So let's look. The change in energy over one cycle is the integral from 0 to t of dE dt dt, which is minus epsilon. Well, now I'm plugging in for dE dt from my expression over there. I get minus epsilon integral 0. Now here I should really write the period we think is 2 pi plus some order epsilon correction that we don't know yet what it is. And then we write the expression for dE dt. So plugging in for x and x dot, you get, well, actually, so look at this. We have x dot times x dot. So there's an x dot squared. That would mean up here, x dot is minus a sine t plus order epsilon. So squaring that, we get a squared sine squared t times a squared cosine squared t minus 1. That's from the x squared minus 1 in the damping. And then dt plus terms of order epsilon, which include, actually, let's be a little more careful here. Not order epsilon squared. Why do I say that? Well, because I've made various errors along the way. That is, my a cosine t was not exact. It had an order epsilon. So in here, the sine and the cosine, both of those terms, the a sine and the a cosine, those are a little bit off by epsilon. When you multiply things out and square and do all that, plus the fact that you have the period a little bit wrong, plus the fact that the whole expression is multiplied by minus epsilon, if you keep track of all that, the worst error you're making is going to be of order this epsilon times these order epsilon errors in the other things. It'll be order epsilon squared. So what I'm trying to say is that this is the dominant term of order epsilon. Then there will be a correction of order epsilon squared. Okay, so now what remains is to do this integral where from now on I'm going to ignore this order epsilon up here because that itself introduces an order epsilon squared error, which, because of this factor of epsilon here, which is already lumped in there. All right, so now let me just erase that so that I can just do the integral calmly. Let me skip the steps, okay? You can do this integral at your leisure. That is, you have to know how to do integral of sine squared, cosine squared. You might have done that in high school or in your first calculus course using sine of 2t kind of identities. Whatever. So let's figure you know how to do enough calculus to do this. Then your answer will come out to be delta E. Actually, I'll show you how I would do it. I'd say delta E is minus epsilon. And then I would go a squared times, I'm computing an average of sine squared t cosine squared t over a cycle. This means average over one cycle. And then times the length of the interval I'm integrating, which is 2 pi. And then there'd be another term, which is minus this. So I have minus 1, a squared average of sine squared t. Again, over an interval of length 2 pi. And then I've memorized that the average of sine squared cosine squared t over one cycle is 1/8. And this is 1/2. So this is electrical engineering thinking. People talk about the DC term. This thing has a DC term of 1/2. That's the average of that over a cycle. This has an average of 1/8. Okay, so this comes out to be 2 pi epsilon negative sine a squared times a squared over 8 minus 1/2. Plus, then there are these order epsilon squared errors that we're ignoring. And now the question is, when is this 0? Right? What is the A such that when we go around the cycle, we have no net change in energy? And you can read it off from the parentheses. That is, a squared has to equal, or a squared over 8 is a half when a squared equals 4, which is when a equals 2. And that is the magic number. That's a very famous number. The van der Pol oscillator for small epsilon has a limit cycle of amplitude 2. X of t is 2 cosine t plus the little correction. So it means that if you were to, graph the waveform of the van der Pol for small epsilon, it just looks like a cosine wave, but it always goes to amplitude 2. All right, so next time I will show in detail how we know that this is stable, and show an improved method than this crude method 1 that's called averaging theory. And I think you'll like it if you haven't seen it before. Okay.